Okay, so what we're going to be looking at here are polar equations and the formulas that come along with those polar equations when we see them on the AP exam. This video will go over just the vocabulary, then there'll be a separate one for a particular review problem that we'll look at. So here we go looking at these terms. Now, a couple of things that you need to remember that aren't calculus related when it comes to polar equations is for most of us, this type of coordinate plane is brand new. What you have to realize when you're looking at a polar coordinate is even though it looks like it's on an XY coordinate plane, what's really happening is we are going around the circle. So it's almost like we're going around a circle to a specific angle and then headed out to a specific point. So what we look at in most of these problems is what is happening from one point to a second point along the path that this particle or whatever it is would be taking. So if I was looking at pi fourths to like 3 pi fourths, this is a pi fourths angle right here, and 3 pi fourths is like over here, looks like that, and we were talking about this curve, then we would be talking about what's happening between those 2 points along the path. It's not like going over or up or anything like that. We are traveling around using angles to describe what's going on, and that's very unfamiliar for most people. Luckily for us, there is a way that we can convert back into from polar equations back into what we call rectangular or regular function form. And these two formulas right here that we have, that x is equal to the radius times the cosine of theta, and usually the radius is the function that they give us, it just has thetas in it. That's how we convert to an x value. You'll notice that there's a formula for the y value as well, how we convert back from from r and thetas back to a y coordinate, which helps us out a little bit. Our y is equal to r times the sine of theta, okay? Another thing that you have to realize, and I'm never saying that they won't ask this question, but for the most part, when you're looking at a polar function, even if you have no idea what the graph looks like a lot of polar graphs end up looking like this, and maybe they do something like that. There's so many different ways the polar graphs can look like, but most of the time, if you just do the integral from a to b of one of those polar functions, it'd be like that. That doesn't tell you the area that exists between that curve and the x-axis, or that curve and the origin. Either way, that's not what the integral tells us. Instead, there's a different formula that helps us find area that we're going to look at in just a second, okay? The other thing that's usually pretty useful is they tell you the interval that they're looking for on these problems. So you're going to stay in regular function form, but when you graph these functions, make sure you change your viewing window to the interval that they are interested in. That actually helps an awful lot to tell what's going on in polar problems. So there's not a ton of vocabulary that comes with polar problems. The first one we're going to talk about is finding the shaded region inside of one polar graph and outside of another. Now for our problems right here, we're going to say R is the one that is further away from the origin. So if I'm looking at two different polar graphs, let's say I have just like a circle right here, then another one that comes out like this. The circle would be the outer one, and the weird function that I just made would be the inner one, the s of theta, okay? To find that shaded region, what we do is we say, okay, we need to find out where the two curves intersect, and most of the time they tell you where the two curves intersect. Then you just do the integral, 1/2 on the outside, or it can go on the inside as well, of the integral from a to b of the function that's further away squared minus the function that is closer squared. And again, you kind of have to know what's happening in the graph, but most of the time it will be pointed out to you that this is r of theta here, and that this smaller function right here is s of theta, and they will tell you those things, so you don't need to worry about, like, oh man, am I getting it right or wrong? You'll also, if you accidentally screw it up and you flip-flop them, you'll get the negative version of the area, just like you do when we're finding normal area, okay? So that's how we find that shaded region. Now, on some problems, if you're looking for the area just between one polar function and the origin, then all we do is we just make sure that the s of s squared, or whatever that is just 0. So really, if it's just one polar function, we still do 1/2 the integral from a to b. We just do the single function, and we square that one, because the other one is 0, okay? That both get asked from time to time, but that's how we find it between two, okay? Now, The next thing that we need to talk about is if we need to find dx d theta or dy d theta, which does get asked for from time to time. What we have to realize in these problems is that the same thing we talked about on the previous slide. My x is equal to that radius function times the cosine of theta. And you just plug that radius function in and then you take the derivative. The problem with that, and it's not a huge problem, but the problem with that is you always have to do the product rule between that radius function and the cosine of theta. And the same thing is true for finding the y value. If I'm looking for the y value, and I have to multiply that radius times the sine of theta to find the y value, then dy d theta we'd have to use the product rule in order to find that. Now, where those come in particularly useful is where we find the slope of a tangent line. If we need to find the slope of a tangent line between, for one of these polar functions, what we do is we find, just like we did right there, where we find dx d theta and dy d theta, then we just put dy d theta over dx d theta and then plug the angle that they give you in to find the slope of the tangent line at that particular value. It usually looks awful. Of all the problems we look at, the slope of the tangent line is by far the one that takes up the most space when you're writing it out. It just looks really bad because that product rule takes up so much space. Lastly, the last thing that they might ask you is where a tangent line, if you're going to draw a tangent line, where is it going to be horizontal or where is it going to be vertical? Okay? The way that we do that is very similar to finding the slope of the tangent line, but if we're looking at horizontal, then what we do is we take dy d theta and we set that equal to 0. An easy way to do that is take dy d theta and then graph it on your calculator and just find out where it crosses the x-axis. If I'm looking to see where the tangent line is vertical, because it's entirely possible as we're going along that I can have a vertical tangent line, there's nothing wrong with that if I'm looking at a polar graph, then I take dx d theta in that particular example and we set that equal to 0. Okay? So, and again, we can just do that in normal mode. We don't have to be in polar mode to do either of those things to find out where the tangent line is horizontal or vertical. So when we look at those things again, that's how we find all of them. Now, the nice thing about polar is, although it's more difficult to understand, there are less formulas that we have to worry about when we're doing these problems. So hopefully this kind of made sense, and if you watch the example of the problem that we'll look at for these, hopefully that'll make sense as well. If you have any questions about this or anything else, please let me know.